wants to learn more about what we do.
All right, a lot of great conversations already starting this morning, and we're going to now follow up to that talk with Mark Hamilton.
Hi, everyone. I'm Mark Hamilton. I'm a freshly minted PhD with Bill Freeman here. I also work at Microsoft, and today I'll be sharing our work on trying to make sense of Dolphin communication. We'll see a few different projects that all kind of take on this theme of being able to try to look at unsupervised data and make sense of it and try to understand what's actually being talked about. So before we begin, we'll first play a little game. Like if we expect to translate something without any kind of labels, let's try to do this ourselves. So here I'm going to play you a little clip of audio from some animal. And your goal as an audience will be to figure out what it's talking about. All right, everyone understand, right? Yeah? All right, let's do it. All right, so who knows what was said there?
They bumped.
Let's knock down the tree.
Yeah, we got some good guesses here. Unfortunately, not correct. But what you'll see is that as soon as you see what's going on in this, it becomes very clear what's happening. So we'll play the clip. So it becomes clear when you watch this that this is penguin for God damn it. This is penguin for like ow, and this is actually the. Oh, it looks like my PowerPoint just crashed here. Well. Anyway, as the PowerPoint is rebooting up, it just kind of goes to show that when you actually see the video, things become so much more clear and easier to understand that there's something kind of special about being able to actually see what's going on that really helps you understand what's being said. With that, we'll kind of jump into a quick overview of the talk. This talk will be in 3 parts. The first will be how we can use machine learning to rediscover human words by just watching unlabeled videos of people talking about things. Then we'll try to apply similar techniques to analyze dolphin vocalization and behavior. And then lastly, we'll try to figure out what in God's name is this system talking about and what has it learned. And the end will be a little bit more speculative, and I make no promises about translating dolphins here. But you'll see sort of how we're thinking about it at the very least. So without further ado, we'll jump into the first section here about rediscovering human words from unlabeled video. And to give everyone in the audience a quick primer, I know that this is sort of a mixed audience, some people from the animal side, some people from the computer side. We'll first talk about what it means to train a system with labels when you actually have the meaning of what's going on here. So you can imagine a big data set here where we've got some audio and we've got some paired labels, like this is the vocalization for dog, it's a vocalization for guitar here. This is our labeled training data set, and then we get a little algorithm here to come stare at that labeled data and learn from it. And at the end of the day, when we give it a new, unseen, real piece of data, we want that algorithm to look at that and then say, yes, this is guitar, and hopefully it's correct in its prediction. And this is great if we actually have labels that tell us what these utterances mean in the real world. But most of the time, in at least the problems that we're thinking of and we're excited about, we don't have any labels that kind of give us that intuition. So we need to be a little bit more clever. And the key idea is to think about self-supervised language learning. And the basic idea is that you take videos and you split them up into their audio and their video components. This is exactly kind of what we did in that game in the beginning. And now the algorithm, instead of trying to predict a word that's labeled, it will try to align clips together. It will try to figure out which clips go together and which audio and frame pairs do not go together. And through playing this kind of a game, this kind of a matching game, you can learn a lot of surprisingly interesting things. How exactly does this do this? This will be a little bit useful to understand for later in the talk. This algorithm will take a look at these different signals of different modalities, and it's going to write down a list of numbers. These are your features or embeddings or representations. So it's going to do this for every single entry in this data set, both audio and video, looking at just one at a time. It's going to write down these collections of numbers, these features, and then we're going to tell the algorithm how to improve its numbers by saying things that go together, aka the guitar sound and the guitar that came from the same video clip, these should roughly be the same collections of numbers you wrote down. And likewise for the dog sound and the dog video clip. And we're going to push apart things that came from differing clips. So we're going to say, don't write down the same numbers for these two instances of sound and frames. And surprisingly, this simple game works fairly well. You can train something on this, and even if you give it if you train with a large enough data set, even if you give it a new utterance pair that you've never seen before, it can correctly associate these two things, like a picture of a dog and the word puppy. So it does a surprising amount of learning just through this simple, unsupervised game. And what I'm talking about here is definitely not new. We didn't make this up. This has been around for a really long time, at least 10 years, that people have been doing these kinds of matching games on audio and video. The one that we focused on in this paper as a baseline was this model called ImageBind by Facebook. Meta. They aggregated all sorts of different modalities and played this trick on a massive data set. And they created these really big foundation models for all kinds of modalities. And so we started there. And we played around with it, and we found some interesting things. And to understand kind of what we found, we'll have to dive into a little bit of the technical details of the architecture here. So the way that this kind of model works is that you take images and audio, you split them into these little patches called tokens. You then append an extra token called a class token. This token's going to have some global context that's going to be learned about the individual clip or piece of sound. And you pass these through these big transformer type models, one for the vision branch and one for the audio branch. And you get these features out at the end of the day, one for each one of the tokens that you pass in. So you've got some spatial tokens, and you've also got this class feature that kind of holds the global state. And if you look at these spatial features, they learn really beautiful, interesting pictures. They learn almost the semantics of the signals that are fed into them. And this class token, that's the one that they actually use to play this matching game. That's the single string of numbers that these algorithms write down in order to play that matching game. And you might ask, what happens with these beautiful spatial features? They throw them in the trash. No need for these. But we kind of wanted to ask the question, what happens when you start looking at these spatial tokens? For instance, if slamming these two class tokens together, if matching them together, performs superhuman at the ability of associating speech and images, what if we slam together the class token with the spatial tokens? Are we going to figure out where the sound is coming from by doing this? No, we're not, unfortunately. Amazingly, even though this algorithm is superhuman at its ability to associate sound and audio through the class tokens, it is not superhuman in its ability to localize the sound. When you say the word guitar, the guitar does not light up here. And this is the problem that we really sought to solve with this first paper. One of the key issues here is that, we're not really optimizing for these spatial tokens to be used in any meaningful way. And so that's the problem that we tried to fix. So we took that ImageBind architecture, and normally it's just taking these class tokens and playing the matching game with them. And we looked into that trash can of spatial features. We did a little dumpster diving, and we pulled back out these spatial features. And we said, these spatial features are almost there. They just need to be aligned together through some nice loss function. So we built this loss function that kind of tries to find matching regions between the audio features down here and the visual features. And the name of this game is that if you find a lot of really strongly matching regions, you're probably found a matching piece of audio and piece of video. They probably belong together. If you play this matching game and you try to look for all these different matching regions and you can't find anything, they're probably coming from totally random clips here. So in terms of actually how we do this in math, we slam these features together to form this big similarity tensor, and we aggregate this down into a single number. The details aren't super important here, but if you're interested, you can talk with me about it afterwards. But you kind of look for all these different matches, and you aggregate these matches together into a single number of similarity, and that's your similarity score for playing the matching game that we talked about. And when you train a system like this, suddenly now these spatial tokens actually really carry aligned meaning between the two modalities. So I'll briefly play a few clips that kind of shows you this. So here is a video, and what I'll be showing you is a paired video with some audio, and whenever I'll be highlighting the regions that this attention is kind of paying attention to when it's listening to this audio, and you'll see them glow in the image. So,
the elephant cools itself in the river. It watches the trees for predators.
So in this particular example, I'll play this again so you can kind of see. And this is also a view of these audio and video features, so you can actually see this happen. You'll see that when the word elephant is said, the elephant just starts to glow. The algorithm is like, that's the elephant right there. Likewise, when river is said, river glows, it says, that's the river right there. So I'll just play it again.
The elephant cools itself in the river. It watches the trees for predators.
And so you can kind of see that these alignments are actually just visible in the features if you view them with PCA. And this not only works in this case, it works with all sorts of different, slightly more non-trivial cases. This one shows adjectives.
Cut the peppers on a wooden cutting board.
So you can kind of see that wood in here is glowing pink along with the other things. So you can actually see this correspondence between words and video in real time. And also, because there's a lot of sound in this data set, you get fun sound correspondences too. Yeah, so everyone's seen that clip, and what's nice is that you can see the saxophone glow in real time. So you get a little bit of language correspondence and sound correspondence. But wouldn't it be nice if we can disentangle these two effects? Like sometimes we'd like to know what's making the sound separate from what that sound is referring to. So what we do is that we take this architecture and we take a playbook out of multi-head attention. We give it another chance to solve this problem. We give it 2 times to solve this problem, and it can figure out how to use these 2 machines in order to solve this problem however it likes. And we'll aggregate those 2 machines together and pump them through the system as normal. So now it's got 2 attempts to find cross-modal connections. And what we find is that with almost no supervised data, just maybe a little bit of regularization here so that they don't turn on and off at the same time, that these 2 heads, they just naturally split apart into sound and language. And so you can kind of see here that in these particular examples, we're prompting it with language. We're saying things like dog, and the dog glows in the language head that emerges, baseball hat, and the baseball hat glows. But if we play the sound of a barking dog, head number 1 will turn on. And it kind of picks one of these heads at random to turn into the sound head and the language head. But it seems pretty reproducible from our experiments. Here's a quick example where I've colored this in a video where one head is kind of the sound head and another head's the language head.
It's okay, puppies. It's just the snow.
And so you can kind of see here when the puppies are barking, they're glowing blue with the sound head, but when they're referred to as puppies, they glow red with the language head. So this effect can be a little bit more non-trivial, it looks like that.
Well, what happens if we have music on top of sound and language? And a third attention head, we did separate, or?
I'm not sure. I mean, we haven't tried that. Probably the results would get a lot worse because it's just the way it goes. But yeah, I don't know. I mean, it's possible. If there's some way to associate like the music and the image. Like in part why this splits out is because sound is also a really great cue of associating.
But just to understand it, the saxophone image, you would have expected the saxophone to be blue in the same way that the dog is blue here.
Yeah. That's a different visualization scheme. It was all just glowing the same color.
But it's the same concept.
Mm-hmm. Yes, exactly.
I think what the question was about, if there are 2 sounds happening at the same time, that there's you would be able to separate them, but that's a different technology, I guess.
So in this particular model, we have this little regularizer that makes it so only one head can be active in one spatial location at a time. It's just to help clean up these visualizations a little bit, but theoretically, it should be possible to separate concurrent things, especially if they come up in different locations in the spatial plane, that this regularizer won't really penalize that so much. It will just penalize the sound and language head both being on at the same time in the same spatial location. So that kind of behavior it can't really support, but other kinds of simultaneous things it can support.
So therefore, it was on one channel, not 2. The barking was on the same channel as the language.
Yeah. So in this particular one, the barking and the language, they're combined together in the audio, and this algorithm is figuring out how to separate them emergently. Lovely questions, you guys. Yeah, so this is like a real 1,000-foot overview of our algorithm called DenseAV that we published in CVPR, I think last year, 2 years ago. And so now that we have this algorithm that at least works on humans, now we can ask the question of like, can we apply this to a more interesting species? And this was really our secret goal all along. We just needed to make sure that we didn't, get sucked down a rabbit hole, that we actually were trying to learn something real. So now that we had that paper out the door, we can now focus in on the dolphins and really think about, can we use a similar system? So we partnered with Denise and Thad. Lovely, beautiful data set of dolphins that has like 3 years. These are just a few examples. Just like this with some clicks in the background. So yeah, this data set is super cool. It's reasonably large, and as Denise mentioned, she's annotated it in a whole bunch of different ways. So it's really, at least of all the data that I've worked with, some of our best chance at being able to apply this flavor of algorithm to this kind of problem. So you guys might be wondering, what happens when you do this, right? Like, what if we apply DenseAV just naively to this problem? And in short, nothing happens. It overfits. There's too many parameters. It's too complicated. It's just a real pain in the ass to get something to work, especially on a small data set. So like, why does this fail spectacularly? For a few key reasons, I think. One is that we've got about 6,000 hours of English videos. If I were to graphically show it out, it would look like this. And Dolphin videos, we have correspondingly a whole lot less, which is quite unfortunate. And also, I think it's just a harder data set in general. The human world has got nouns, it's got knives and cutting boards and wood and potatoes and all sorts of interesting things that are very, very visually distinct from each other. Whereas the dolphin world has like water and maybe the occasional noun, like this piece of seaweed here. But it seems to be a little bit more about actions, that this might be the way to chisel in this problem.
Did you train it on the union of all the data or just on the dolphins?
We've done a few different tricks. We tried pre-training on humans and then fine-tuning on dolphins. We tried a few things.
Just to understand, what you were dreaming of is that whatever the dolphins were talking about, nobody understands that, would start glowing.
Yeah, exactly. And there's also some caveats why this kind of failed in that we trained on a single random frame from the videos because we don't have that much compute, so that's exponentially easier. But in the case of dolphins,
What do you mean you don't have compute?
you gotta dig it up. You gotta find it somewhere. And I work at Microsoft, and I still, we had a bunch of V100s, and they were okay, but also, like, I'm lazy as a grad student, so it's hard. It takes a long time. And I mean, I had to train that DenseAV system like hundreds of times to really get it to work quite well. So, it just takes a lot, and there's not a great like pre-trained video backbone. At least there wasn't back when we were doing the work. We used these image backbones. There's also a lot of minutia about which image backbones work for this that I don't really have time to get into. But if you peek under that rug, you'll find a cabinet of horrors down there. But yeah, we could chat about this later. There is some ways that we can get this to sort of start to work, and that will be in sort of the latter part of this talk now that we're coming into.
Sorry, can I ask one more question? So when dolphins are vocalizing, like with clicks or whistles, the dolphins don't even, because I feel like there's detectors for dolphin audio and there's video recognition for dolphin. So I'm struggling to understand the combination of those two things.
I guess maybe I would describe it like, how when OpenAI dropped ChatGPT-2 or GPT-2 and everyone's like, wow, this is really interesting. What a party trick. It comes up with news articles about unicorns and everyone like went their separate ways. And then they scaled it up by another like K orders of magnitude and suddenly now it's like smarter than everyone in this room and like doing everyone's homework and ruining the whole everything. And so there's like this order of magnitude.
But the question is, if you play those dolphin videos in the original system, do the dolphins light up? Well, you dreamed that what the dolphins were talking about would light up. But the question is just, do the dolphins light up? Is that what you're asking?
Yeah, exactly.
And do they?
Yeah, so basically what we get in that system is that, like, in order, the prerequisite for it to beautifully start working is First, that it's able to match these audio and video clips together in a novel test set that it hasn't seen. And what we found when we trained it is that it was not good at doing that matching. And so first the system needs to figure out how to do the matching, and then once it gets really good at doing the matching, it starts to actually figure out like how to do the matching. And we weren't even seeing step one. This thing
Why is a dolphin harder than a saxophone?
Dolphins so many ways to answer the question.
No, you can talk about
Only inappropriate.
matching behavior with audio, right? I mean,
We were matching frames with audio, and so it didn't quite have that full behavioral context. That might have been it, and we've since improved. So we'll talk a little bit about that. Yeah.
So just an understanding question. In like the standard videos with human language, if
Yeah.
you had like a video of a guy and a dog, and the guy says, "This is my dog," light up, or would the dog light up?
So I think that the guy lights up on the sound because he's like making the sound, and the dog lights up on the reference head. Yeah.
Different colors.
Well, and like I guess with dolphins, I mean it didn't work yet, but with dolphins, if they're referring to something, it's like ambiguous as a dolphin.
You'd hope that, like, through enough training, it would come out in the wash. It hasn't come out yet in the wash, but yeah, that was the goal with that architecture, is to try to make something that could possibly solve this problem.
So is the complication just that you trained it only on dolphin data, and then every single video has some combination, or?
So I think that there's a few complications, largely stemming from the lack of data, just because, and also it's harder data and it's less, like, you know, the videos of humans are a little bit more direct. Like usually when they're talking about something, you see it as well and it's quite clear, but with dolphins, there's a lot of dolphins around. They may or may not be talking about something right there. The thing might not be on camera. You have this whole 3D world. So it's a lot less clean. There's a lot of different ways that make it exponentially harder to solve the problem in that case. Yeah. So, you know, if you think about the kind of situation we had, we kind of took this unlabeled video of dolphin and we split it apart into audio and frames, and we tried this and it didn't work spectacularly. At least it was kind of overfitting on certain aspects. So we thought, like, you know, what would be ideal to have here? Like, ideally, you know, you talk to a dolphin researcher like Denise, and she looks at these things with a very particular eye. You know, she sees, these are mottled and spotted. That's connoting a certain age. They're touching. They're playing with seaweed. They're by the surface. Maybe they're playing. Like, she looks at it with this entirely different lens to actually looking at this problem that had been like honed over years and years of study. So, you know, realistically, one of the thoughts is like, if we could just get this kind of annotation on every single frame, you know, maybe we would stand a much better chance. And so, you know, we asked Denise, I know that you've annotated some of the data, but how about you just do this kind of an annotation for every single frame of the data so that we can really have something nice to train with? And she gave me this look and said, absolutely no way. This is crazy. This is like 400,000 clips. Like, there's no way I'm doing that. And you know, so we said, we'll have to turn to our friend here that's you know, doing our homework for us all the time, ChatGPT, to actually automate and scale out this process of labeling. So that's who we turn to, and thankfully ChatGPT never tires, and so we can just throw it thousands and thousands of frames. So what we do is we take these videos and we chunk them up into frames and we give them to ChatGPT in a little like film strip sort of thing, and we ask it 72 plus different questions all about dolphin behavior. Anything that it can see visually, we ask it. This has been informed from Denise and her work and from a bunch of other researchers, things that might possibly hold the secret to what these dolphins are talking about. And so, you know, ChatGPT can take a look at this frame and it can answer these questions. It can answer them 10 times per frame to get different attempts and shots at it. It can give you confidences on these that you can then average together to even get a little bit better. You can do a lot of really fun things, and with our infrastructure, at Microsoft, we're able to get about 432 million labels in 24 hours through this sort of process. So we can annotate every single frame with these 72 questions, and we can ask it to describe the frames in text. We can ask it to do all sorts of different interesting things that might be useful, and some of the labels are a little bit iffy. You know, some individual answers hallucinate, but when you average them together, it gets a whole lot better. So here's like a few examples of some of the spotted behavior. We've got playing with seaweed, digging in the sand, breaching and jumping out of the water. The presence of juveniles, it's actually like not terrible at, surprisingly. Group diving behavior, even if it's looking at the camera, we can see when it's coming and checking out the researchers. So ChatGPT is able to do a fairly reasonable job at spotting things, almost like an okay to good intern would if you really turn them loose on this data set. And some of the things, yeah.
Wanted to ask, did you validate any of the output with humans?
Yeah, so there's some amount that we had these little small test sets that I worked on the prompt with. And you can also just, I'll show a little bit later, I have this little UI that you can just explore all the different labels and see. And soon we'll be adding a little components that we can manually say yes, no, to these kinds of labels. But at least from eyeballing it, it looks pretty reasonable, which is nice. And yeah, so it can, you can just very quickly get a high-level bird's-eye view of your data set this way. And so some of the best use cases are for super rare events like bubble rings, which occur roughly 1 in every 4,000 clips. For things like synchronized leaps, this occurs 1 in every 100,000 clips. So these super rare events can be just like pulled out of your data set in a fairly automated way, so long as you just give ChatGPT enough description of how to look for these things, which a little bit of prompt tuning can go a long way when it comes to this kind of thing. But what's nice is that you can train the model in English the same way that you would train your friend or your intern to do this kind of a labeling task. So it's fairly flexible, and you can very quickly understand whether or not it will work. Some of the worst use cases are when it's a little bit more nuanced, like are dolphins touching in this example? I don't know, maybe. And ChatGPT is similarly befuddled. It says like, oh yeah, I think there's definitely dolphins touching, but like, there's some complex geometry here that ChatGPT is kind of sliding under the rug, and maybe they're touching, maybe they're not. Hard to say. So some of these things that are a little bit hard to tell visually will also be hard to tell for ChatGPT visually as well. So it's not without its limitations for sure. And I'm sure I could make a whole PowerPoint on the limitations of this kind of a thing, but it's a first guess. It's at least it can provide a reproducible, unified approach that's kind of testable and very quickly done. And so now, if we come back to our architecture, we can make it a little bit simpler by A, using nice pre-trained models, and B, adding in some of these annotations alongside the frame embeddings. And these annotations, it's mainly from ChatGPT looking at the frames themselves. It doesn't also get audio paired along with it. So it's just kind of like enriching, featurizing that frame video with features that are coming straight from the minds of the best dolphin researchers in the world here that are possibly helping the algorithm find this thing. And now this is at least doing 60 times better than chance. So it's finding something that's connecting this audio and this video together. And now our goal is to figure out part 3, what in God's name is going on here? What are these things learning to be able to solve this task? And I'll briefly say that in every single talk, right, you kind of start out and the whole audience is following you, and then maybe somewhere a little bit in the first quarter, you lose about half the audience, and it keeps subsequently halving until at the end of the talk, even I don't know what I'm talking about. And that's here. That's this stage of the talk right now, so get ready for it. We've done a few different things. Sorry, question?
Trying to understand the dolphin speech. Did you strip out noises that are not in speech itself?
Yeah, so that's actually one of the things that kind of helps is that now we can also ask, I didn't mention this, but we can also ask ChatGPT to look at this audio and say, is there anything even here worth looking at? We can have it look at the spectrograms. We can say, are these whistles, are these clicks, are these buzzes? We can do a similar style analysis. We don't give that to the video branch just because it's like cheating in some sense. We don't want it to we want to keep these two branches separate so that this cross-modal effect works. But we can use that to say, focus in on things that are actually there in the spectrogram. That helps a bit.
I was actually more concerned about the other way around, because things like you showed the examples of dolphins jumping out of the water, or those air bubbles, or things splashing, or so on. then you might not intentionally recognize the sound of water splashing and say, okay, this means that the dolphin wants to jump.
Absolutely. Yeah, that is like entirely, probably in a lot of different cases, what this algorithm is doing. Like, for instance, it can, we'll see later in the predictions, when we look at some of what it predicts well, I filtered out some of the ones that are clearly environmental, like it predicts but you'll see it predicts the depth of the dolphins quite well, probably because it can hear the difference between deep dolphins and high dolphins, not necessarily because of the vocalizations. It can predict when you're on the boat or off the boat quite well, right? Because they sound very different. When your camera's above water and below water, it predicts those things quite well. So some of these spurious things we try to remove, like any above water stuff we try to get rid of. Just to focus in on the stuff that is more important. But for sure, things like other kinds of behaviors that also make sound, like splashing, will come out linked together by this algorithm, and it won't necessarily be because of language.
To be sure, 60 times better than chance in associating the audio to the right frame. When you have half of the questions that is like the right association and half that is random association?
Yeah, so in particular, what's this 60 times better than chance? Like it does, it gets an accuracy of 6% on a 1,000-way retrieval task. So you give it 1,000 random frames and random audio clips from encounters with dolphins that it's never seen before. You got to make sure you do the splitting properly so that the test set is just entirely different encounters, entirely different days on the boat. And it does like 6% when it's this at 1 on this 1,000-way retrieval task. It gets up to like 23% when it's at 10. So these are kind of some of the numbers that we look at to ascertain whether or not this is associating these things together. And granted, this is much worse than the human stuff. It's not nearly as good at associating as the model for human stuff, so it's still a harder data set, but we're now at least starting to get something that can generalize at least a little bit.
What would be the comparison to the humans? Like, so this is 60 times better. What would it be if you were using human data?
So our at 10 metric here is like 23, and our at 10 metric for humans, for the human data is like 70. So, yeah, and granted that 70 is superhuman ability to link them together. Like you would not be able to solve this task of listening to a random YouTube clip and figuring out which clip you just listened to because the data is noisy and whatnot. So the algorithm performs at a superhuman level. Yeah. And it's probably performing at a superhuman level here because you can't listen to a random clip of a dolphin and figure out which clip it came from unless it's a very small set. But if you're given 1,000 clips, good luck. It's a 1,000-piece jigsaw puzzle. So this is now the last part of the talk where we're going to try to figure out what's going on. So, everyone first, they just look at the embeddings. They reduce their dimensionality using an algorithm called t-SNE and just take a look at how they look like. So here I'm going to show two plots, one of which I've colored the embeddings based on what kind of communication the dolphins are doing. So this one is the probability that there's a click somewhere in this data set, and you kind of see these clicks are clustering in this little group down here, some up here. Likewise, the same t-SNE plot, I'm going to highlight it for whistles, and you can see whistles cluster in different aspects of this embedding space. So you can kind of start to see this emergent separation of different communication types when you look at these embeddings. But hard to make heads or tails of this. Yeah.
Sorry, just so I follow, each dot in this is one of your video-audio pairs.
Yeah. And so in particular, what this is I've taken these audio embeddings, and these embeddings are like 512 dimensional. I've reduced them down to a little 2D map so that you can look at them with your normal human eyes. And then I've colored these dots based on whether or not there's a click somewhere in that snippet of audio or a whistle somewhere in this snippet of audio. And the dimensionality reduction, you'll see that they're both the same shapes because this is the same piece of data just colored in two different ways. And it's a little bit hard to see with the light, but hopefully you can see that they're in different places, which is the main takeaway. Cool. So this is great, but it's a little bit hard to understand, like make heads or tails of. But if we remember those labels that we have for these clips, those labels that have been figured out by looking at the video, what if we try to predict those from the audio? And so what I'll show is some of the select labels that I think are least likely to be due to weird noise. And what I'm showing is the balanced accuracy. So these labels have incredibly different baseline rates, and if I just showed accuracy, everything would be really high because these are rare events, so it doesn't really make much sense. The balanced accuracy, what this is showing is like you take the accuracy of the true events, like the events where this thing happens, just look at that set, what's the accuracy there? And you take the accuracy of all the events where this is not happening and look at that particular accuracy and you average them together. So it's sort of like this accuracy metric that's balanced between the classes. And if you do the smart thing, which is predict just the baseline, the majority class, you'll get 50% on this test, right? So 50% is kind of nothing smarter than a simple baseline, but everything above 50% is like actually something statistically useful that it's using to predict these kinds of annotations from the frame. So a lot of the bars are actually high, and like, what can it predict from the audio? Well, it can predict the audio labels. That's fairly easy, but it can also predict other interesting things, like their depth, right? Whether that the surface, bottom, or middle, those seem to be quite predictable, largely possibly from environmental factors. We'll still need to tease that apart. But I'll briefly draw your attention to these two, digging in the sand and side by side. I'll show examples of these later, so just put a pin in that, remember it. These ones you'll see little spikes on the predictive thing, so this algorithm is able to predict these better than chance. And we'll see what those actually look like a little bit later in the talk. And so, once you have this plot like this, you have to actually start doing some detective work to figure out what it's using. It's really hard to do this if you're just sitting there like typing Python commands. So we figured we need to actually build a website here. And I'm going to now attempt to demo this website live. And, pray for me, because the demo gods are mean. So this is our FinFinder application. It's kind of like Google for Dolphin. And the idea here is that this is every single clip in Denise's database, kind of all in a single Azure Search instance. And it's able to be filtered by LLM predictions, our audio predictions, clusters that we were shown previously, things like the dataset examples. And so we can very easily, we come into the LLM predictions, they're grouped by dolphin behavior. We can do things like, let's say we want to find all the dolphins playing with seaweed here. We can just move this up. So these are things that now, these are kind of very clear dolphins playing with seaweed going on in the data set. So these are all the different instances where ChatGPT says, yes, these are dolphins playing with seaweed. And if we click on it, we can see a little more details. We can play the actual clip from where it originated. You can kind of see, yes, seaweed there, very nice. And, but this actually goes a little bit deeper. We also have the audio features, those ChatGPT looking at the audio frames, and we can do things like, let's find all the whistles in our data set. So come over here, move this slider up, and you'll see a bunch of clips, but it's a little bit hard to tell. And we switch to the audio view mode. Now you've got audio vision. You can see all these different clips. So if we take a look at some of these things, like let's say we look over here, maybe we want to say, this is an interesting pattern. Let's find something similar. We can press to find similar, and now it's going to use those deep features to find all these sorts of instances in your data set where this pattern emerges. And if you want to make sure you only look at different encounters, you can press this box, and now you get, on a different day, a different trip, similar kinds of whistles, but in totally different contexts. With this kind of a thing, now you can start to actually dig into these labels. So I'll do this live here. We'll take a look at that digging in the sand things. Let's come back to frames. Let's go to our LLM predictions. Let's go to dolphin behaviors. Come down to, does anyone see it? Digging in the sand down here. We'll dial this up to, let's say, 0.6. And now we'll see these are all instances of digging in the sand. And what's more, we can say, let's try to find things where we were able to predict digging in the sand. So I'll come to my audio predictions, same thing. And now we're going to look at the cases where we have been able to predict digging in the sand from the audio. And I'll also look at only the testing data set, so I'm not cheating. So these are all the different clips that it's able to predict correctly digging in the sand. And we can now look at the audio and take a look, and we start to see some of these patterns that maybe the algorithm is using to solve this problem. So we kind of see these large sweeping things that these are kind of the dolphins echolocating on the ground and looking for food down there. So we come take a look at one of these clips, you'll be able to see it. So you can now kind of see this. Then the algorithm is kind of picking up on this fact that there is some regularity that it can use to predict key behaviors. In this case, researchers know about this kind of thing, so it's not like super novel. But what is nice is that the algorithm was able to discover this kind of behavior, and we were able to, with a few moves of sliders, find this kind of thing in our data set. So if I return back to, great. So we've kind of seen this example of digging in the sand. Another thing that's really fun, and this requires a few more dials of the sliders, is the side-by-side one that was clearly predictive. And when you start looking at these examples, you can narrow your search down so you're looking at smaller groups of dolphins. And you look at these, what's able to be predicted. A lot of them have this pattern of these little tiny snippets of communication between two individuals here. So I'll play this clip. So you can kind of hear these dolphins like squeaking back and forth to each other in these little bits. So the algorithm is able to identify like, this is probably a dialogue between two dolphins and they're right side by side. So also kind of could possibly be picking up on mother-calf relationships and things like this. So these are some of our preliminary discoveries here that we've been teasing apart. And of course, we're going to be overlaying some of the class activation maps to really make sure that it's looking at these particular things and not other structures in the audio. But we at least now have this kind of a system where we can start figuring out what these algorithms are learning just by clicking around a website, which is quite nice.
I just want to clarify something. This is getting the side-by-side from the acoustic, right? Or is it getting it from both?
The way that we did this is that I basically looked at these examples where, the ChatGPT looked at the video and said, these are two dolphins side by side. So, yeah, that's clear. But then, we were able to predict it also from just looking at the audio. So we look at these examples where like the prediction was correct, that the algorithm was successful, it correctly found something useful. And then we look at like all these different clips and we just kind of look at them by eye and say, does anything pop out? Just as a first order of business here, and this is what popped out to me, is that there's a lot of these kinds of little chatty communications going on between dolphins that I think this algorithm is kind of keying in on. And so, next we're going to try to integrate kind of interpretation style approaches so we can see what these algorithms are actually attending to in these spectrograms to solve these problems. And hopefully we'll get a nice picture like DenseAV, where these particular parts of the spectrogram where these chattings occurring are like lighting up or something to that effect. And we can also do things with the Uhura codes to try to associate these kinds of behaviors as well, so we can see what parts of the code are carrying this meaning, hopefully. Yeah.
So I'm just curious, and this is really brilliant, super cool. Have you looked at because in theory it seems like having to ground meaning should be a lot harder than just like describing what's going on in general, right? Which is also like what ChatGPT is doing, because you're doing the whole. So have you looked at things like just audio captioning or something, and whether that would be more accurate than a model that like has to ground things?
Yeah, there's certain different ways that we get some amount of grounding just by ChatGPT. So for instance, with these audio clips, when I show ChatGPT the audio clips to predict clicks and whistles, I actually, box it up and say, this is second 1, second 2, second 3, second 4. So don't just tell me where the clicks are. Don't just tell me that there are clicks. Tell me which boxes the clicks occur in. So you can do clever things like this to localize. Like one of the things I'm thinking of doing next is using an off-the-shelf dolphin detector to just draw boxes around the dolphins and then say, ChatGPT, what is dolphin 2 doing here? Like, how does dolphin 2 relate to dolphin 1? And then, it would sort of have that knowledge embedded in it and would be able to give some kind of an interesting answer. When it comes to like off-the-shelf captioning for audio, I would be a little bit more skeptical just because like it doesn't work on dolphin. You know, it's like something trained on human won't necessarily apply to dolphins. We're using OpenAI Whisper, which was trained on humans, but we do a few things to kind of massage the signals into the right structures so that OpenAI Whisper will be able to take it and at least understand it as a pre-trained model to give us some reasonable features to play with. But we still have to fine-tune that backbone a little bit to get it to pull out nice predictions. So I don't know if that answers your question, but hopefully towards.
I mean, just to be clear, like it mostly does, but I was thinking like, you know, you can fine-tune an audio model, or like a captioning model, to predict the labels that you got from ChatGPT.
Yeah. That's more or less what I'm doing. In that the architecture is kind of. Let's see if I can go back to this architecture. Yeah, this is the architecture, and you'll see this audio branch is OpenAI Whisper as a backbone with a small adapter. OpenAI Whisper has been modified with LoRa, a low-rank adaptation, so it's more or less what you described, which is take a big, fat, smart human model that already knows lots of things about sound and tweak it a little bit so that maybe it can start to adapt to Dolphin.
Yeah, I was also going to mention, it is just so hard to know which dolphin is vocalizing. You know, you'll get to that point, but then it's like, it could be anybody. One of the things, you don't have these data yet, we don't have it either, but we're looking at some of the 360 cameras who now do audio localization, because we've designed like custom things and they're just challenging in themselves, but some of the new technology might let us give you certain channels with certain orientation on the video, because it's still a curse as to know who's vocalizing. So you can get to a certain level right now, but I think that's what's going to spur it on in some ways.
And like every new additional channel of signals is just like a new interesting problem that we can co-correlate and all put together. So maybe we can find something nice.
So the ChatGPT, one way to think about it is a magic box does this thing for you.
Yeah.
But another way to think about it is that it's Denise.
It's like a crappy Denise, yeah. Like it's very high throughput, but not as good as Denise, right? Like, and doesn't have the full context, but is like a poor man's approximation to Denise that at least can be applied tirelessly on every frame. And it will get better. Like the IQ of ChatGPT, of these kinds of models, rose from 90 to 120 in 1 year. So yeah, it's crazy.
So you've loaded to it all of Denise's labelings.
Well, Denise helped me make a nice prompt. Denise, gave me all the things that she's looking for. She gave me this ethogram, and we looked at this ethogram together. We asked ChatGPT even to look at this ethogram and say, what would you likely be able to predict just from looking at a frame? And then we say, here's a bunch of information on dolphins and how to spot different behaviors. I want you to spit out this big JSON payload with all the different answers in it after taking a look, and try your best not to lie. Lives depend on it. If you put that in, it will be a lot better. And then, that's the more or less prompt. It's a super simple prompting thing. You just write a reasonable thing as if you're trying to train an undergrad to do it, and don't expect anything more than an undergrad in terms of performance, but it's still better than nothing.
But you're aspiring to do more than Denise because you want it to light up the parts of the image that the dolphins are talking about, which Denise can't do from the listening. Is that right?
Well, so, the way that I kind of think about it is that ChatGPT is able to kind of enrich our data with interesting behavioral things. And then, actually fine-tuning this whisper model, that is what we hope to actually start to learn associations. Because, ChatGPT can't figure out with a translation of dolphin because, it's just not designed for this kind of thing. But we can train models using similar tools that is, used to make ChatGPT. But we can train our own models to try to understand that audio using ChatGPT's visual understanding as a guide. Just because we can train ChatGPT to look at these videos and at least be somewhat like a dolphin expert.
Just on the point of adapting general audio models, these tend to be trained on YouTube, which is really, YouTube, it turns out, is like 50% speech and 50% music. And speech is really focused in a particular frequency range. Music is really targeted towards that same frequency range that we really react to. And we've had a lot of trouble getting this sort of like pre-trained off-the-shelf models to work terribly well on bioacoustic data. So specialized training, I think, really, really does help in this area.
And we've used your models too. So in some of our analysis, we use a surf perch. We can chat after about how to, I don't know, use it to its best of its abilities. But I've used a lot of the tricks that you told me in our call. Like, namely, one of the key tricks you need to do to get this to work a little bit better is that these Dolphin clips are 48 kilohertz sample rates, and you give them to these models that sort of telling it's half the sample rate. And now it's a longer clip, but it's lower, and this kind of shifts Dolphin into the audio range of a human. And this is also a great tip if you're trying to listen to your Dolphin vocalizations. Suddenly they get a whole lot more human intelligible when you do this little trick. And also, the algorithms seem to perform better, at least in terms of the metrics, when you do this trick as well. But I think there's plenty of tricks in this.
You watch it in slow motion. And then,
yeah. More or less, you're listening in slow motion in some sense when you do this trick.
Yes, so I guess somewhat related question. Another thing that is very different in the unlabeled settings between the human videos and this type of videos, besides having dolphins in them, is that it seems like human videos tend to be produced in some strong way. Right? You are seeing something specific, you are seeing a scene, you are seeing someone talking about something. Did people try doing something like putting a camera at Central Park and training on human speech, not from a video that is meant to show something, but just from random short interactions?
Yeah, no, I think that's definitely one of these things what makes the Dolphin data so difficult, because it is not, beautifully shot by Wes Anderson or whatever to, show exactly what the director wants to convey. It's just, shot by a bunch of people who are swimming down there and trying to capture as much as possible, but the sound is coming in from every which way, and there's dolphins over here, dolphins over there, and dolphins change really fast. There's sometimes like 40 of them wriggling in a group together, so it is really messy in terms of like stuff for an algorithm to figure out, whereas the human data is definitely a lot more narrative, and that certainly helps the development of grounding, which is kind of why it's so hard to get this stuff to work on the Dolphin data.
You could try that on human data as well.
Yeah.
You could do the same experiment on something that you do understand.
Yeah. If there's a large enough data set of like, I don't know, observing humans, you could do a similar thing and see if the results hold up. And I mean, the back of the envelope is that it's just going to be a lot harder to get it to work so nicely. That in some sense it works really nicely because the data has this signal in it. But when you start getting into the more natural scenarios, it starts getting harder and harder for this grounding to develop.
So I had a question about like human in the loop, or like in terms of like a next step, because I think the thing that's been fascinating with CETI's annotators is that they're almost getting better in the same way that humans taking time and spending time and then seeing the errors and then improving on those errors. So is that part of the plan? And also, just as an aside, branding-wise, there's already like 3 software programs called FinFinder. So
great.
Just in case you want to...
If anyone has a good name, let me know. I literally asked ChatGPT, come up with some snazzy Dolphin search engine, and it said FinFinder stuff. If you have another one, let me know, because I would love to have a snappier name for this.
I'm sure you'll come up with something great, but... So, like the sort of human in the loop, I don't know if that's reinforcement learning or... I use the term wrong.
So far, I've been the one in the loop, but what I'll add is the ability to kind of really quickly, control select the videos and bulk edit the annotations, so that we can start actually putting in some human ground truth into this system, more than just me looking at it and sanity checking it for the first few loops. That's definitely something that's.
But that platform allows for it, like you say, with the.
Software is soft, so we can make this thing do anything we like.
Yeah, that's awesome. Thanks.
This is super cool. Question about the sperm whale in the room, I would say. What if they're not talking at all about what they're doing, right? Because in this case, there is a lot of dynamics there. So you can imagine kids at the park, they are talking about what they're playing. But, for example, sperm whales are going to be a lot more like old men playing ball, like pétanque, and they're just playing and talking about something else. So is there a way in which you could sort of say, well, we do not know whether we can say anything about this, in a Bayesian way?
Yeah, that's a great question, and one that's it also happens in the human data set that you train on. Like there's a ton of clips that you can't match together. And the idea is that with enough data, some of these come out in the wash. But also you'd like to be able to associate as many of these things as possible. So some of the things that I've also played with are like predicting future, predicting past, predicting aggregates, predicting all sorts of other things. These things tend to be a little bit harder to predict, but they're still somewhat predictable. But like you can give it just through this contrastive task, like all sorts of different scenarios. Like, can you predict what they're going to do in 20 minutes? Can you predict what they have done? So I've done mainly aggregate queries, so I'll get back to you on this. But the aggregate queries are aggregating both in the past and the future. It's kind of like instead of predicting the value of whether they're diving right there, it's like whether they're diving within a 30-second interval around that particular utterance. And what I found is that it's a little bit harder to predict than the actual line signal. But more study needed before I may say anything strong about that. But now is basically, if you guys have any ideas about what we can possibly predict or what we can ask about these Dolphin video clips, like, please let me know.
In that regard, in the human version, so you have a video of someone cutting something at a cutting board, but they're actually telling you a story about their grandmother who's not in frame. Is there a way for the failure videos, whatever percent it is that don't work, to then detect the subset of these are videos that failed because the audio is referring to something else? Do you see what I'm saying?
Yeah, at least with the human data, you can see that like it's not like super confident at finding a match. Like it doesn't find a particular match. So you can do certain things like this. One kind of architecture that you can do that maybe we'll start to get at this is that right now we're using this dual encoder architecture where the image branch and the video branch don't get to see each other. And this is because it's a lot easier to train because you can featureize the images, featureize the video, and then slam all pairs together. But you can imagine a slightly more advanced architecture that sees both an image and a video, chews them both up together, and then predicts whether or not they belong together or not. And this is much harder to train because you can't just do all pairs with, regularly you can do all pairs with 2K evaluations, with K is your batch size. In this kind of a thing where you have a joint model, you need K-squared evaluations. So it takes a lot more evaluations of that network to actually get it. And also, now the signal is kind of twice as big, so to speak, so a lot more attention too. But, a system like that could perhaps indicate its certainty that these two things are linked together, as opposed to just saying, like, I really hear grandma, I really expect grandma, and then just like swing and a miss when it tries to align with the audio. So that could be an architecture that could start to get at that type of question.
So a question for, we really empathize with the earlier about saltwater chewing things up and the difficulties of this. But now that you've been really immersed in this data set and you've had, it almost seems like we're in parallel worlds here. We have Shane on SETI and, he's constantly asking him to annotate things and look at things, and you have Denise here. And we've been thinking also about like the ultimate data sets for machine learning. So now if you could kind of take all these lessons learned up until this point and see what you've created here, like how would you chart like, a dream scenario or data set from this now with all these lessons learned? Like what would be your being, dream at this point?
Yeah, I think that some of this analysis was done because we had a lot of things from Denise's labels, but they weren't like quite aligned as strictly as we might need for machine learning. So we had these like beautiful annotations, but they were kind of only the starts of the behavior, not the ends, so to speak. So like this is one example where it's a lot nicer when you have the start and the end of a behavior in like some dense segment, because then you kind of know that this is where I should be able to see some kind of a correlation. So this is like one instance where we really would love to have these like, dense timeline style annotations, but it's hard to do that. I think another thing is like, I would love to start getting individuals into the mix, like really verified individuals. Like Denise has done a lot of this with the data set. what'll be interesting to see is like if analyses like these can even like help individual detection in this kind of a scenario. Like for instance, you know, a human can say, this is soot, but sorry, it's probably not soot, but you know, whatever. and then as it progresses in time, maybe a tracking system can follow soot around so that this label can stay fresh for a little bit longer. But it's hard to tell what exactly is going to be useful just because we don't know what they're talking about. But I'm sort of thinking that the best approach is to annotate a whole bunch of stuff and then see what's predictable, see what's actually like useful for this prediction, and then dig in that way. So I know that was kind of like a ambulatory walk around things that might be useful for labels. Also, you know, just getting them in a nice clean format that researchers can use and having a rough amount of quality on this. Like sometimes the quality of data is exponentially more important than the quantity of data. When you're doing self-supervised stuff, it's you can kind of know that it's reasonable quality, and like with this ChatGPT stuff, you at least know that the labels are coming from this particular frame. But you know, if the labels and the frames are shifted, you know, suddenly now this throws an extra wrench into the machine that, and these algorithms are already going to have a hard enough time finding this really, you know, low signal to noise type stuff. So, and removing any of those kinds of barriers is also really helpful when curating data sets. Oh, and finally, you mentioned that CETI has got a bunch of data annotation needs. I have in the last slide, if you've got that data annotation needs that you want to throw into this ChatGPT system, let me know and we'll just throw it in. So
you're not done with the talk, you're...
Yeah, I'm basically done.
Oh,
basically
done.
done.
Oh, sorry.
This is like, you know, the recap slide, and then we'll be done. So you picked a good time to pepper me with questions. Yeah.
So I have a question. So, for example, like what you mentioned about that you have partial and not full annotation from the beginning to the end. You could probably stitch things together, but then it would be sort of synthetic data. And in general, you could probably generate, based on this stuff and methods out there, diffusion, whatever, generate synthetic dolphins with annotations. Is that going to be useful? Well, we don't know how much that counts, but is it the data still that's your bottleneck, or is the quality? And you can use methods for cleaning it up, I assume, also the quality.
Yeah, like, you know, one of the things that we hope to do is like figure out how to improve the quality of data with this kind of thing so that it can help researchers make better quality data as well. Like, I think that there's a fairly broad amount of possibilities you can have. Like, if you have a smart human that's augmented with a machine that can at least follow directions pretty reasonably. And you can be creative with like how you do this. So there's a really big body of work that could possibly be done in this direction. And in terms of like generative data, you know, that's like a whole nother can of worms that I didn't even talk about. But like, you could imagine if you had a really nice like joint generative sound vision system that, in the same way that I'm trying to chisel away at signal by looking at what's predictable, you could chisel away at the signal based on like what was created from this system that learned on the entire data set. And you know, one thing that's nice about those is that you see these examples of like one-shot style transfer, one-shot, you know, Studio Ghibli-ifier. And these diffusion models, they're quite good at being adaptable. So these kinds of things might be also a very reasonable path for a researcher to take to kind of chip away at this mystery.
Do you think it might help to throw weird stuff in the water that the dolphins might talk about in more specific detail?
You know, I feel like
His favorite.
I was skeptical of this at first until I saw Denise in there with the scarf, that she has a little red scarf that she waves around, and those dolphins go wild for this red scarf. Like, they took this thing and they're putting it on their fin like a little cape, and they're diving around, and all the other dolphins are trying to get this scarf, and they're playing hard to get with it. You know, one dolphin even went up to someone else with a piece of seaweed, and it's like, please play with me. Like, I don't have the scarf, but I have this piece of seaweed. So, you know, these foreign objects, I think they really do love. And I found one example in this data set where it's like a sunken IKEA furniture, and they're all like playing with this thing. They're all like gathering around this piece of IKEA furniture and chatting about it because they're whistling and making little sounds and things like this. So at least it looked like a piece of IKEA furniture. So I think that, you know, with any of these enrichment things, you'll probably get interesting behavior out. And Charles Ramey, a THAAD student, has like all sorts of crazy research on this with otter toys and fun things that enrich animals that are foreign. But
Yeah, I had a question, probably a simple technical answer, but how do you avoid associating videos and audio just by the duration of the file? There must be clues in the latent space about how long the clips were.
Yeah, so I've standardized it so I just extract these little 5-second windows of audio and video. So they're the same 5-second windows, and I've like re-encoded them so that there's hopefully not signatures there, but there are still signatures. Like even the rough color of the water can kind of give you hints at this. The quality of the camera can give you hints at this. And these things can certainly confound and explain some of this 60 times better number. But you hope that your data augmentation strategies make this really difficult to do. So we do a lot of like different audio augmentations, like pitch shifting, corrupting, noising, circular shifts. Also with the image side, we do a similar amount of image augmentations just so that it's harder to use these clues, that the clues that remain after this augmentation are actually relevant and semantic as opposed to cheating. But these systems cheat whenever they are given the option to.
Thanks so much. This is a really cool talk. I think one of the things I just want to really underline from what you've done here is showing, hey, supervision is actually really, really powerful. And I think one of the really cool things here is that you're using ChatGPT to multiply the expert effort to get more supervised signal, right? And often, I think we heard yesterday, we go to unsupervised methods because we're like, man, it's really hard to get labels and stuff. But if we can find ways to multiply that effort, there's potentially a lot that we can pull out of that.
Yeah, absolutely.
Yeah, I just want to thank you for an excellent talk and for a great morning. We now have a lot to talk about for lunch, so we went about 10 minutes late into lunch, but we still have an hour, 20 minutes. So enjoy, same as yesterday. The food should be out here. You could eat outside together, and we'll kick off in an hour and 20 minutes. Thank you. Cool.
Just thanks to these folks who made this project possible. Andrew Zisserman and John Hershey couldn't be here today, but they have been